Hi, my name is Samba and I work for Career Booster Technologies. So welcome back again. In the previous video, we have seen a bit of an introduction to the TCP IP. We just went through just speaking about the network user to user and then network to network, and we touched upon the basic topologies of what is followed in a small office or medium office or enterprise network, right? And I think we laid a good foundation for us to go forward into the TCP IP. So with really say TCP IP, Transport Control Protocol IP networking model, what is this all about? It is nothing but a model which refers to a set of documents, and what these documents are describe function required for each network. Like I said in my previous video, it takes a lot, okay, to really see that a packet comes from one device, reaches the destination based on whatever the information it carries. Apart from the user information, there's a lot of control information which makes it to reach the destination accurately. So it describes each and every small function. Then everything that should happen for a computer network to work. So it's a simple of that. So when we have all the functions working according to a specific model or protocol, you know that it's functional, right? The computer network is functional. So obviously it has a list of protocols to recommend under each layer. So what is a protocol is nothing but a set of logical rules that devices must follow to communicate. And also talks about the physical requirements, be it the physical layer, or be it the connector, cables, media, you name it. So what it takes to really put together a TCP IP based network, it speaks about that. So if you see an overview, so TCP IP contains essentially 5 layers. So you have an application here, okay. So you have an application here, you have a transport, you have an internet, and you have a link. So essentially TCP IP contains 5 layers, okay. This was the original model, but later what happened is you have another model coming up, which is a current one, right? So you have application, transport, network, data link, and physical. Okay. So what is the TCP IP? TCP IP is a model essentially contains 4 layers or 5 layers rather. So you have an application, transport, internet, and link. This was the 4 to begin with. Later the link portion is split into 2, data link and physical. So in terms of the purpose and the functionality, it remains same, except that we have a 5-layer model currently being followed compared to the original one. So they have a direct relation. The old and new in terms of comparison layer to layer is exactly same, except that the link layer has been converted into what you call data link and physical, right? Now there is another parallel model which is followed, is called OSI. All of you must be knowing, especially if you are a computer science graduate, you know this better. So you have a 7-layer model. So we have physical, data link, network, transport, session, presentation, and application. Okay, and in some of the videos and they say how to remember this easily. So they say that please do not throw sausage pizzas away. So that's the first letter of everything. Okay, so I repeat, it is please do not throw sausage pizzas away. But I think once you start working, you'll remember this. You don't need any such help. But looking at all 7 models, the bottom 4 are typically take care of the actual transmission of the what you call packet or the data, whatever you say. Physically, it's very clear that's the only physical link we have. Data link plus networking have their own identities to reach the immediate hop or the final destination, and transport ensures the end-to-end communication being that much more reliable, and more importantly, they also identify which application that is being currently followed. So together, they take care of the flow of the data, whereas the upper 3 layers, application, presentation, and session, is the application for which the network is being put to use, right? So you have like a protocol like HTTP, Hypertext Transfer Protocol. You have a protocol like Telnet. You have a protocol like like say DNS, or you have protocol like Secure Shell. You name it. There are many protocols that are come into the application. So they directly address the subject or directly address the application of the user for which the network is being used. Now the question always comes is how these two compare itself with each other. OSI, which is a 7-layer model, and TCP IP, which is a 5-layer model. How do you compare them? Which one is better? So there's some sort of a discussion that typically happens. But the fact actually is that you don't have to really compare and then choose which is better one. Both are relevant. Actually, they in a way complement with each other. If you see, the OSI model is typically the reference model. It doesn't have any specific protocols being listed as a part of it, but rather very clearly it defines what each layer is responsible for, right? For example, if it's a physical, it's all about the transmission media, electric, optical, or wireless. It could be the pinouts and the connector. It talks about the cable. It talks about the transmission speeds. If it is a wireless, it also discusses the modulation methods, whether it is a phase modulation or a frequency modulation or a amplitude modulation is not used in data communication a lot. So, but mainly it is frequency and phase modulation. And then you have multiple access techniques like FDMA, TDMA. So that's a wireless word. So it's all about how exactly the information which is coming from the upper layers need to be physically transmitted. What media we use, at what speed we generate, and then what's the type of connector we use. If there is a connector, what are the pinouts, which pins are transmit, which pins are received. And also you have what you call the cable being discussed, right? So that is physical. Data link, typically it's about layer 2. Layer 2 does starts with the framing, and then it does the physical addressing, identifying the next hop. You may have a destination which is probably several networks away, several routers away. But what is your immediate hop? Like a PC to a router interface, router to another router. So identifying the next hop is often done using the physical addresses. So it takes care of that. And finally, not to forget the error detection. So the packet as it is received at the receiver, data link is the layer which identifies whether the packet has come the way it has been sent by the sender, or are there any transmission errors, like one's becoming 0, zeros becoming 1, or whatever is it. So it detects that if it is not happy that the packet has come not cleanly, there are some transmission errors, it will drop, it won't pass it to the upper layers. But if it is fine, it will send. So that's the data link layer, right? Framing, physical addressing, and error detection. Network layer is all about logical addressing. It stamps the from and to addresses on every piece of information. We call it as a packet that leaves a particular device, making it reach the destination in spite of following any path. So once the information has been added with the header, added with the IP header or the network layer information, that means that packet can go anywhere. Simple example is a letter with an address written on it. Suppose you post a letter with a clear address written on it anywhere in the world, and I'm clear, anywhere in the world, it will reach, right? Up to the right stamp value has been to be used. So that's a different question. But at least that packet has become self-sufficient in terms of, okay, let me put in any box, let me be mixed with any other letters. Still, whoever picks this letter know exactly where to forward it. That is the information, that is the ability the network layer will give it to any information. Say that, hey, here it is coming from and here where it is need to go. Now, transport layer is all about opening up a connection so that you negotiate how do we decide whether the packet has reached the destination or not. There is an acknowledgement system. At the sender side, each packet is being given a sequence number. So you have a sequence number with acknowledgement number ensuring that the packet has been reached and there is a way it can acknowledge. Now session, presentation and application are into the application as far as TCP IP is concerned. So session layer is all about opening up a session, for example, ensuring that all the transactions that happen in a session have an identity at a session level, right? And then that negotiation happens, and then at the end of the session is terminated. Presentation is all about formatting or coding, whether it should be a text format. If it is a text format, what coding is to be used, whether it's an ASCII or any other type of coding that we need to follow so that the information is readable or it can be interpreted easily by a human user. Application is fundamentally an interface between the user and the network. So if a user has a thought, he wants to send a message to someone, how do we do this, or how he or she will do? Maybe probably open up a webmail or put a message into it and then fill up the relevant fields of to address, put the subject. And that is handled by an application level protocol called SMTP, Simple Mail Transfer Protocol. Or it could be a POP, Post Office Protocol, or it could be HTTP. You want to browse a particular website, you have a browser, and then when you pick a particular put the URL there, the website address, and you want to browse it. So there's a protocol called HTTP, Hypertransfer, a text transfer protocol, right? So these are all applications because the application layer is the one which says, okay, you give it to me, I'll take care of the rest. I'm giving an interface to you. You can key in your information and I'll get you the information you want to. I'll take this packet to the destination, and when the destination responds back, I know how to show it to you. So that's the application. So clearly there is a function, right? Everywhere there is a very clearly laid out function for each layer, and they all work together to make the communication possible. If I compare to the TCP IP, it matches one-on-one, except that the application is taking care of application, presentation, and session. Now what's the difference? The OSI is the reference model. It clearly tells what each layer should do. That's what we just briefly discussed, 1 or 2 lines for every layer. Whereas TCP IP clearly lists down a specific protocol. For example, we have a network access, probably it's an Ethernet is one of the finest example of that. So Ethernet talks about the physical layer, Ethernet talks about the layer 2, but it doesn't limit itself saying that this is what should happen. No, it says this is how it happens, right? So Ethernet says I can transmit at 10 Mbps, 100 Mbps, 1 Gbps, 10 Gbps. And typically I use a connector called RJ45 which has an 8 pins, and in that, depending on the device, whether it's a PC or a switch or a router, there's a clear-cut understanding which pins are transmit, which pins are receive. Ethernet is a wired network. It could be optical or electrical. Then it talks about the cable. It has 2 types of cable: straight through cable, crossover cable. So it's very specifically told. Coming to the layer 2 of Ethernet, which is data link layer, it has a header format where it has a preamble for the framing. Then you have the destination and source MAC addresses being clearly represented there. Then there is a protocol type field telling the upper layer, that is layer 3, whether it's an IPv4 or an IPv6. Then you have what you call an FCS, frame check sequence for error detection. So very clearly made out, and there are limits for the user data that it can carry, 46 bytes to 1500 bytes, something like that. So it has a very clearly laid out protocols. You go to internet, you have an IPv4, IPv6 where the formatting, everything is specific and clear. Transport layer, you have a TCP and UDP, transport control protocol, user datagram protocol. So there are 2 choices. Application, there are many. For example, HTTP, SMTP, Simple Mail Transfer Protocol, POP, you have Telnet, you have SSH, you have DHCP, you have DNS. There are plenty of protocols in the applications. So how they support each other, these 2 models? So perhaps as a beginning, one need to be familiar with an OSI model, trying to understand what should happen at each layer. But if you want to implement it, you walk over to the TCP IP, pick a protocol of your choice which suits your application, which suits your need, and implement it. So it's almost like a specification document. It's a protocol document, right? So it's like a difference between a friend who tells you how to reduce your weight and a doctor or a dietitian who helps you how to reduce your weight. What your friend says typically, if you want to reduce your weight, so he may suggest you should exercise, you should take a healthy food, avoid all junk foods. He may say, but he may say very generically, right? He may not say, he may not specify what kind of an exercise you should do, what type of food you should take or avoid. But when you walk up to a dietitian or maybe a gym trainer or one, they will tell you specifically what to do. They said, okay, you must do a brisk walking for about 45 minutes every day, something like that. And then dietitian will say that what are the foods to be avoided specifically, how much you should eat, what type of you should eat, how many times you should eat. You're getting, so that gym trainer or dietitian is like a very specific, like a TCP IP model. Whereas your friend is like an OSI. Both are important. So there is no competition between them, according to me. They just aid each other. So every time you go to OSI to know what should happen, TCP IP you will know how it need to happen. As simple as that. Okay. So what these layers do actually typically, if I go by the OSI layer, what these layers do actually is everyone has a function to do. To that extent, they add some information. So there is an original application user cannot go on its own, right? So there has to be some information saying that this is the kind of an application it is. Here it is need to be formatted in so and so. This is the size of the file, etc. I have broken that into few pieces, so this is how it is. So it has its own control information added. Similarly, when it goes to transport, network, data link, and physical, everyone have their own information added. And when it goes to the recipient, the control information will help the receiving machine to piece together all this information. It will join all this together, packets, stitch them together, and to see what the original application was. So apart from the user data, a lot of control data will go, and that's what the protocols are all about. So let's see slightly in a generic way what exactly can happen when someone follows a TCP IP or an OSI model. So typically at an application level, I'm starting from the top, the information may be very large, right? So you have a user data, you have a very large. And it is not wise enough, or it is not possible to send the entire data in one go. That doesn't help. In case that data goes bad, somewhere down the transport layer, you may have to retransmit all over again. So that is not efficient, I would say. So as a result, what happens actually, the information is broken into smaller pieces, and we refer that as segment. So this is the original raw data. It is now divided into so many pieces. You see, automatically there is some information which the user must carry, okay, saying that along with that, otherwise the receiver won't know how to join them, okay, how to join them. So there is an information there, but for the moment, you know, the piece by piece information that goes out of any device is this one single segment. So this segment will become a user data, right? This is one piece of data. Obviously, it is not the full data. There is some amount of segmentation being done. There is a lot of presentation and session information is added to it. So it has what you call an application header, right? So the original user data is user data. It has had some control information to help the receiver to understand how it need to interpret this. Now user data along with the application header will become user data for the next layer, which is layer 4, which is transport. So transport layer has its own job, reliability, multiplexing applications, etc. all that. So it has its own header added. And when you add the transport header, this fellow is referred as segment. And when I add transport and user data together, it becomes a user data for the next layer. So which is very clear. Now when it goes to the layer 3, the user data is not the original user data. User data along with the application header, along with the transport header will become the user data for the layer 3. So what does the layer 3 do? It has its own header added, right? So what is this typically address? The logical address, clearly giving the values where it is coming from, where it need to go to. Now along with the IP header and the user data becomes a user data for the layer 2. So when a layer 2 goes, it has its own header added, and it is the only layer in the TCP IP where it has a trailer to. So this is FCS, frame check sequence, or CRC, cyclic redundancy check. So this helps the error detection, whereas this helps the other functions like framing and physical addressing. So what we have seen just now in this slide actually is we call it as a layering encapsulation. So original data is cut into pieces, and each piece is given some amount of control information, some amount of header being added at every layer, and this goes to the physical layer and it travels forward. So let's see a bit of a what you call animation in terms of what happens in each layer at the transmitter, at the receiver, at the sender and the receiver. So the sender we have a 7-layer model, and at the receiver also we have a 7-layer model. Only thing in sender it starts at layer 7 and goes down all the way up to layer 1. In receiver, layer 1 first gets the data and goes back to the layer 7. Now going by my previous slide of layer encapsulation, this is what exactly happens. So each layer adds its header, the original information is taken, header is added, and finally when it touches the physical layer, it is converted into ones and zeros. The packet travels there, okay, the frame travels there. An opposite action happens here. Layer 1 see, okay, this is the ones and zeros I have. I'm happy with the physical condition, ones and zeros are easily recognizable. I go to layer 2. Now in the layer 2, it studies the header and trailer attached. Once it is happy, it passes to the layer 3 by taking those headers away because it has done its job. So similarly, when it goes to layer 3, whatever the blue one here, the layer 3 has added, that will be interpreted. If it is happy that it is the recipient, it will pass to the upper layer. So whatever happens here, opposite happens here. Which means what? If there is an information added by the application layer will interpret it. If there is an information added by the transport layer, for example layer 4, that fellow will read it. If there is an information by the layer 3 will read it. So though they may not have the physical connectivity is always there between layer 1 and layer 1. They have what we refer as a logical connection. Every layer at the sender believes that he is connected or she is connected to the corresponding layer in the destination. For example, when we write a letter or we send an email, how do we refer it as? You say, I sent a mail to my friend, right? How can you say that? Because you feel that you are connected to him directly. Whatever mail that you have written is supposed to be opened by your friend. That means at an application level, something has been written, application will read it. Similarly, somewhere down the layer, an IP header puts a IP header saying that from and to address. So the IP layer at the destination will read it. Oh, this is it is coming from, and this is the destination, which is me. So everyone has an information for their counterpart, but they are not physically connected. The only physical connection is this one. So whenever you say you sent a mail to a friend, you sound as if you have personally handed over a message on a piece of paper. No, right? That's not the way. But in you doing that, whatever information you had put in, that will be interpreted by your counterpart there. So what you see, these are all dotted lines, are all logical connections, whereas this is the only one physical connection, right? For the next set of videos in the prerequisite videos for my training, I'll be explaining some of them slightly at a high level overview, but layer 2, layer 3 we'll go in deep, okay, because that's our main focus. Routing and switching are layer 2, layer 3, okay. As a technology, we'll focus more on that. Okay, so that's about the layering encapsulation, right? So I'll stop the video here. So this is just a bit of a TCP IP OSI comparison. We saw like what are the layers are there, how they are referred as, and what's the comparison between OSI and TCP IP. The next video will start speaking about layer by layer, and I'll be taking specific examples for each layer to explain how TCP IP works and is implemented. Okay, thank you.